Hello students, welcome to my channel. In this class, I am going to teach you internal direct product of groups. The definition of a internal direct product of groups and a theorem related to it. This theorem is very important for examination point of view. So let us proceed to the topic. Now, definition of internal direct product of groups. Let G be a group, H1, H2 be two subgroups of G. So, we are taking two subgroups H1, H2. Then G is said to be the internal direct product of H1, H2. H1 and H2. If any x belongs to G, any x belongs to G can be expressed as the product of an element of H1 and an element of H2. That means here x belongs to G can be expressed as product of H1, H2 for some H1 belongs to H1 and H2 belongs to H2. This is definition of internal direct product of groups. Related to this, we have an important theorem. The statement of the theorem is like this: if G is the internal direct product of two of its subgroups H1 and H2, then the only element common to both then the only element common to both H1 and H2 is the identity element that we have to establish. In the first part, if G is the internal direct product for two of its groups H1 and H2, then we will get only one element that is common to both H1 and H2, and that is the identity element of G. The second part we have to establish: G must be isomorphic to the product of the set subgroups H1 cross H2. So that we have to establish. So now let us proceed to prove this theorem. Now you see proof of the theorem. Let A belongs to G and A belongs to both H1 and H2. This implies A inverse belongs to H1 and also A inverse belongs to H2 as H1, H2 are subgroups of G. Are subgroups of G. So we are taking G is a group. From G we are choosing element A, and suppose A is common to both H1 and H2. Now, as A belongs to H1 and H2, A inverse also belongs to H1, A inverse belongs to H2. Because H1 and H2 subgroups of G, by inverse axiom, definitely A inverse belongs to H1, A inverse belongs to H2. Now, G is the internal direct product of H1 and H2. So, any x belongs to G, any x belongs to G can be expressed as x is equal to h1 into h2. We are we have G is the internal direct product of H1 and H2. So any x belongs to G can be expressed as x is equal to H1 into H2, where H1 belongs to capital H1 and H2 belongs to capital H2. Because here this is G is the internal direct product of H1 and H2. So any element belongs to G can be written as the product of first element belongs to H1, second belongs to H2. This expression is unique, and this expression is unique. Now x is equal to H1A inverse H2 we can write, where H1A belongs to H1, A inverse H2 belongs to H2. As the expression is unique, as the expression is unique, we have H1A is equal to H1 for H1 belongs to H1. So this gives us A is equal to E. But we have taken A belongs to G and A also belongs to H1, H2 common to both. This shows that the only element common to both H1 and H2 is E belongs to G. The first part of this theorem is proved. Let us prove the second part of this theorem. Given G is the internal direct product of H1 and H2. So any x belongs to G can be written as x is equal to H1 H2, where H1 belongs to H1 and H2 belongs to H2. So given G is the internal direct product of H1 H2, so any x belongs to G can be written as x is equal to H1 H2, where H1 belongs to H1 and H2 belongs to H2. To prove that G is isomorphic to H1, H2. Let phi be a mapping from G to H1 cross H2 such that phi of x is equal to order pair H1 H2, where X is equal to product H1 H2 belongs to G. So, in order to show G is isomorphic to the product set H1 cross H2, we have to define a function that we have done here. Phi is a mapping from G to H1 cross H2, such that phi of X is equal to the order pair H1 H2, where X is equal to H1 H2 belongs to. Now to show that phi is 1 1. Let xy belongs to G. Then we can write x is equal to h1 h2, y is equal to g1 g2, where h1 g1 belongs to capital H1 and h2 g2 belongs to capital H2. So we are taking now two elements. In order to show the function phi is 1 1, how we will show a function is 1 1? Now we have to take phi of x is equal to phi of y, and we have to establish that x is equal to y. Let phi of x is equal to phi of y. This implies h1 comma h2 order pair definitely is equal to g1 comma g2 order pair by definition of a phi, because the function phi is defined in this way. So this implies h1 is equal to g1, h2 is equal to g2. So h1 h2 is equal to g1 g2, from which we get x is equal to y. This shows that phi g 1 phi g 1 1. So the function phi g 1 1. Now let us prove the function phi g on 2. Now to prove phi g on 2. Given G is the internal direct product of H1 cross H2 and phi is a mapping from G to H1 cross H2 given by phi of x is equal to H1 H2, H1 belongs to H1 and H2 belongs to H2. So in order to show the function is on 2, we have to choose an element from H1 cross H2, and we must show that there exists a preimage in a G by which the function phi will be on 2. Let this is order pair. H1 H2 belongs to H1 cross H2. Then for this element, let H1 H2 belongs to H1 cross H2. Then for this element H1 cross H2, we find X is equal to H1 H2 belongs to G, such that phi of X is equal to phi of H1 H2 is equal to how much? Now H1 comma H1. So H1 H2 belongs to H1 cross H2. Then for this element we find X is equal to H1 H2 belongs to G. So that phi of X is nothing but H1 phi of H1 H2, which is the order pair H1 H2. So for this element in the product set, we get X in G. This shows that phi is onto. Now the function phi is onto, and that we have proved here. Now let us proceed to show that phi preserves the composition. To show that phi the composition. To show that phi preserves the composition, let xy belongs to G. Then we can write x is equal to h1 h2, y is equal to g1 g2. Where h1 g1 belongs to h1, h2 g2 belongs to h2. Now phi of xy. So we have to show that phi of xy is equal to phi of x into phi of y, by which we can say phi preserves the composition. So this is equal to phi of h1 h2 g1 g2. This we can write phi of h1 g1 h2 g2. This we can write h1 h2 g1 g2. This we can write phi of x, phi of y. So we are getting phi of xy is equal to phi of xy. This shows that phi preserves the composition. This shows that phi preserves the composition. So this shows that phi preserves the composition. So we have proved phi is 1 1. The function phi from G to h1 cross h2 is 1 1. Then the phi function phi is 1 2. It also preserves the composition. Hence GG isomorphic to h1 cross h2. Proved. So G is isomorphic to h1 cross h2, and we have proved the theorem. So with this class is completed. In my next class I will meet you with a new topic. Till then, goodbye.